General relativity, step by step. Last time I evaluated the stress energy scalar T, which had this particular formula here, and the components of the stress energy tensor with one upstairs and one downstairs index to be these expressions here. This was the time component here, and all three space components, that's the r, the theta and the phi components, all had this particular expression here, all the same. And we'll see later that that will save us a huge amount of time when it comes to solving the field equations. Just want to remind everyone that this expression here is specific to this particular set of coordinates that we've chosen, the t, r, theta, phi with the co-moving r. And it's also evaluated for the cosmological fluid, which has density ρ0 and pressure P0. Okay, I'm going to pinch in a little bit and I'm going to write down the field equations. We had different forms for the field equations, but I'm going to write it down like this: equals 8 pi g multiplied by t mu nu minus a half g mu nu t. Let's just remind ourselves what everything is here. This is the Ricci tensor here. That's just a constant. That's Newton's constant, universal constant of gravitation. That's the stress energy tensor in these particular units that we've got here. Half is just a number. G is the metric tensor, and that's the stress energy scalar. And so I think we know the right hand side. Yes, we know what the metric tensor is. I've still got my maxima session here, so I can scroll up and down. Yeah, that's my metric tensor with two downstairs indices, and I've evaluated the Ricci tensor here, but I'll use my notes rather than this one. Okay, so we know the right hand side, and well, we've got expressions at least for the left hand side. However, when you look at this equation here, we've got t mu nu with two upstairs indices, and my expressions for the stress energy tensor has got one upstairs index and one downstairs index. So we need to change that. And what I'm going to do, I'm going to multiply on the left by mu alpha and on the right by mu alpha. We're going to multiply on the left by the metric tensor with two downstairs indices and sum over index mu, which is this one, and summing over index mu, which is that one there, which will have the effect of raising and lowering, with one upstairs and one downstairs index. Let's have a look. So it's r alpha mu, no, that's not mu, that's a nu, equals 8 pi g t nu alpha minus a half, and then here we're multiplying one metric tensor with upstairs indices by a metric tensor with downstairs indices, and they are matrix inverses of one another. So it comes out to be a Kronecker delta nu alpha times stress energy scalar T, which is unaffected, of course, by any of this index raising, Blanc. And we know everything now. We know everything now. So let's just have a look at this. Let's have a look at we've got four components here because the Ricci tensor is diagonal. Let me just remind myself that that's the case. Yes, here's the Ricci tensor. Here's the Ricci tensor according to maxima, which has got two downstairs indices. So, which has got two downstairs indices, and we are looking for the Ricci tensor with one index raised. So let's just have a look at how that might work. Well, this is what we need. We want this. But we've got the Ricci tensor with two downstairs indices. So I need to multiply by, we want an alpha and a nu. We're going to contract with a beta. There we go. However, because the metric tensor here is diagonal, and this one here is diagonal, the only term that we need to worry about is when alpha equals nu equals beta, I guess. So all that does, that's dead easy to do. All we do is to multiply the Ricci tensor by the corresponding element of the metric tensor with the upstairs indices. So let's have a look at what that is. That's LG for downstairs indices, so it effectively means dividing by these numbers here along the diagonal of my matrix. Okay, so that says that R00 equals G00 times R. Did I have upstairs or downstairs? I had downstairs, which equals -1 times the corresponding entry of the Ricci tensor here, and I've got the copies. I've got that up here somewhere. If I pinch in a little bit, it's quite a long while ago. Here they are. No, it's there. It's there. It's these terms here, and what I'm going to do is I'm just going to write them out. I'm not going to go backwards and forwards and up and down. But I did evaluate these 2 screencasts ago, I think. So it was -3a double dots over a. Where is it? -3a dot dot over a equals +3a dot dot over a. R. Oh, I say 00. I've been a bit slack about this. Sometimes I'll say RTT, and sometimes I'll say R00 because the 0th argument or the 0th index is t for time. I'll try and be consistent. I'll replace them with t's. So we've got GTT times R downstairs TT, and that equals R with 1 upstairs and 1 downstairs T. R equals G superscript R, quite a lot of R's in that, which equals what? Just a minute, I need to scroll up a little bit. Here's my workspace. This one here, but of course I need the matrix inverse because this is my metric tensor with 2 downstairs, lower, L for lower, 2 downstairs indices. So I need to divide by a of t squared, not multiply. So it's 1 over a squared times what? Well, I'm just cheating. Well, I'm not cheating here. I'm copying off my notes. It would be nice to scroll all the way up to find that Ricci tensor and scroll all the way down and write it down, but that's we're going to be here all day. 1 over a squared times a dot dot plus 2a dot squared minus 2q dash dash upon q. And I think that's it, isn't it? Yeah. There we are. So there's the first component done. R time radius, we need theta, equals g upstairs theta times r downstairs theta. See, these are not properly formed tensor equations because I'm choosing a particular coordinate to go there. This isn't a description, that is the theta coordinate I'm talking about. It's this term here I need. So it's 1 over q squared a squared times, that's the theta coordinate, and I'm copying from here, that's 2q squared a dot squared, what a nightmare, plus q squared a dot dot minus q dash squared, oh dear, minus q dash dash. Better watch out that my q's don't start looking like a's. I'll write that a bit more neatly. Q dash dash plus 1. In all of this, a equals a of t, Hubble expansion parameter, and q equals q of r, which is a non-flat, a measure of the non-flatness of the space. I better close that bracket there. And we've got the other term here, which is r phi equals g phi times r phi equals, and I think it's the same thing. Because if we go back here, it's not immediately obvious from the Maxima output, but this one here is just a factor of sine squared, oh there it is, sine squared theta times this one here. So we're multiplying by sine squared, and indeed dividing by sine squared at this term here, because we're dividing by, instead of dividing by q squared a squared, which is this term here, we're dividing by q squared a squared sine squared. So we're multiplying and dividing by sine squared to get to that term there. Now let's work out what the left hand sides are. Well, that's relatively straightforward because I wrote them down just up here. So we've got the stress energy scalar T, and we've got the time components which are here. So let's just write down what we've got here. It's equal to, copying from here, 8 pi g. I say sometimes I'll write c to the 4 and sometimes I won't. Over c to the power 4. Sometimes I'll implicitly assume it's equal to 0. Times, oh, it's this formula here I'm looking at. So T mu nu, which is the 0 component I'm interested in, so it's minus rho 0. Is it plus or minus? It's minus lambda over that, minus cosmological constant upon 8 pi g over c to the power 4. So that's that bit there. Minus a half, the delta is 1, times the stress energy scalar T, which is this term here, so it's minus plus minus. Can I get it all on the same thing? Not quite. Not quite. Minus a half of minus rho plus 3p0 minus rho plus 3p0 minus, what was it? 4 cosmological constants over 8 pi g over c to the 4. 4 lambda over 8 pi g over c to the power 4. Well, that's great. That's multiplying by all of that, I guess, there. And that equals, well, let's do the cosmological constant first. That should be dead easy. We've got minus 1, minus times the minus is a plus, and 4 over 2 is 2, and 2 minus 1 is 1, and the 8 pi g over c to the 4 cancels. So that's quite nice. That's just a single cosmological constant there. Let's do the rho 0 term here. This will be multiplied by 8 pi g over c to the power 4, and let's have a think about that. We've got a rho 0 term and a p 0 term. Let's do the rho term first. We've got minus rho, minus times minus is a plus, so it's minus a half minus rho 0 over 2, and what have we got here? We've got minus 3 over 2 p0. So just tidying up that a little bit. I'll get rid of this. I'll get rid of this here and write it in a bit more neatly here. Okay, where were we? It was the cosmological constant plus, and then what did I have? I had minus, there's a half there, so it's 4 pi g over c to the power 4 times 3p0, which way around? It's rho 0 plus 3p0. That's nice. Oh, so we've got the first term. That's great. Now we'll have a look at all these other terms here. All of these other ones are the same. Why is that? It's the same because I very carefully considered the equations with one upstairs and one downstairs index. And so that has got the very desirable property, certainly in this coordinate system, that the time component is here, but all 3 space components are the same, which is really, really, really convenient. And we'll be able to use that fact to simplify our algebra enormously in the next screencast. So let's just write it out. What have we got? We have got, these are all equal to, from this equation here, 8 pi g upon c to the power 4 times T mu nu for the spatial components is now this one here, P0 minus cosmological constant. So it's P0 minus cosmological constant over 8 pi g over c to the power 4. That's that term there. And we've also got minus a half times the stress energy scalar. What's the stress energy scalar? It's this thing here, blom, blom, blom. Can I fit it? Can I see it? Not quite. and it was minus a half, wasn't it? So down here, minus a half times, oh, it's here, minus rho 0 plus 3p0 minus 4 cosmological constants over 8 pi g over c to the power 4. Plus that. Getting a bit, yeah, equals, well, how many cosmological constants have we got? We've got minus 1 plus 2 is a whole cosmological constant. We've got plus 8 pi g over c to the power 4 times what p naughts and what rho naughts have we got here? We've got a minus a half rho naught minus rho naught over 2. And what about the pressure term? We've got plus 1 here, minus 3 over 2. So it's minus p0 over 2. Is that right? We've got plus 1 here and minus 1.5. So it's altogether minus. Oh, well, that's made our life a little bit easier. So I can get rid of these things here and rewrite them in a more civilized way. So that's going to turn into a, can I get rid of that? That's going to be a 4, and the term was p0 plus rho 0 if it's a minus. It's a minus p0 plus rho 0. And how many cosmological constants did I have? Just one. Right, okay. So what have we got? What have we got now? We've got the Einstein field equations have got 4 non-trivial components that correspond to the diagonal of the Ricci tensor. This one here for the space components, and 1, 2, 3 terms, all of which have got the same left-hand side, and we'll use that fact in the next screencast. Stop there. Stop.